Welcome to our webinar series for the ClimTip project. This is a project about the uncertainty-aware quantification of climate tipping points, funded by the European Union. We do this webinar series to talk about various aspects of climate tipping points and invite different scientists, including early career researchers like today. We have Sjoerd Terpstra from Utrecht University, who will be talking about the abrupt shifts in CMIP6 models. And quickly to introduce Sjoerd, he has a bachelor's degree in physics and master's in computational science. And now he's a PhD candidate at the Utrecht University, focusing on climate tipping points and their interactions. And I guess it's a timely webinar because his paper, the one that he is a lead author in, was published just last week. And it's exciting to have him to present this research results. The floor is yours, Sjoerd.
Yes, thank you very much for inviting me. Hello, everyone. I'll talk about the paper that we just introduced. It's the assessment of abrupt shifts in CMIP6 models using edge detection. So let's shift that slide. So it's a little bit of a background. What do we mean when we talk about abrupt shifts? So according to the IPCC, the abrupt shift is defined as a change that takes place substantially faster than the rate of change in the recent history of the affected components of a system. So it's really something on like a short time scale for a certain system to change quite a bit. Now in this figure, you can see example from a paper where they looked more specifically at tipping elements. And these include things like circulation in the subpolar gyre, different type of ice sheets, winter sea ice, but also some things on land like the Amazon rainforest or the boreal forest. And the idea is that at least some of these systems, when they tip, they might undergo certain called abrupt shifts, so they might change quite rapidly. But at the same time, there are also some other systems, for example, Arctic summer sea ice that are not necessarily a tipping element, but they may still show some type of abrupt shift behavior, which is the focus of our study. And we frame this research a little bit in the terms of global tipping point reports that came out in 2023, where they assessed for each tipping element whether they would tip, but also whether they would show some abrupt behavior. So we comprehensively check at each of these subsystems that are represented in climate models to assess whether these abrupt shifts take place in these models or not. And the reason is that the risk of the occurrence of these abrupt shifts is still quite uncertain for many systems, but it's also quite uncertain when this system might undergo such a shift. As a little bit of a background, there have been some other assessments going on in a similar area. One quite known one is the one from Dryfoot and others in 2015, which they looked at CMIP5 models, which is a previous generation of climate models, where they make a catalog of abrupt shifts in different systems. And they found quite a substantial amount of them, and mainly in systems related to the ocean and sea ice. 5 years later, Sebastian Baggiani, which is one of the co-authors of this paper, wrote a paper on developing methods to automate searching for abrupt shifts in climate models. That's the so-called edge detection, which is the method we use in this paper. And they also scanned with that method the CMIP5 models and obtained similar results as the Dryfoot paper. Another paper that I will mention later on is the one from Armstrong-McKay in 2022. And this was more a literature review and assessment of different systems that might undergo tipping. And what they nicely did was give some type of global warming threshold or estimate at which different systems might undergo a certain type of transition. And recently, there's also a preprint out of Angevara and Dryfout again, where they look at strong nonlinear surprises, which is also some type of abrupt shifts, also in CMIP6 models, but they focus on slightly different data than we do, which I will get into later. So the research goal is to assess the presence of the abrupt shifts in CMIP6 models. And we do this catalog according to 3 different criteria. So we focus on subsystems identified as tipping elements. Then we look at the ones that are unclear tipping elements. And finally, at systems that are not categorized as tipping elements. So tipping elements include things like the Amazon rainforest or the subpolar gyre. Unclear tipping elements include monsoons and Antarctic sea ice. And the not tipping elements includes the rest of the sea ice systems. Even though we structured in this way, with this research, we really look at whether things are abrupt. So we don't make a claim whether it's actual tipping behavior we see. Just want to try to show whether these shifts happen, and they might originate from some tipping behavior or from some other feedback mechanism. So the dataset we use are all the CMIP6 models that did the standard deck of experiments. So these are state-of-the-art, fully coupled climate models that simulate almost all the Earth systems. Importantly, they do not include interactive ice sheets. So that is one system that we don't look at that might undergo abrupt shift. And we chose to look at the 1% CO2 scenario. So it's a scenario of quite high forcing. It starts at pre-industrial CO2 levels, and then it increases its CO2 level with 1% every year. So it's that over 150 years of simulations, you have a quadrupling of the CO2. But it is quite strong forcing. So you can see the whole range of systems behavior in future climate change. And for a reference data set, we just use pre-industrial control simulations. And what we do, we focus on two-dimensional variables. So these are in the ocean, atmosphere, and land. So these are things like surface air temperature for the ocean, for the atmosphere, near surface air temperature or precipitation, and for land variables, things like leaf area index, so coverage over the ground of vegetation. And we compare data year by year. We do this on yearly average data sets, but we also compare month by month. So we look at changes from January to January to January, for example. This is relevant because some systems are quite season dependent on what type of abrupt shifts they might show. Now, as I mentioned earlier, we use the edge detection method that Batiani developed. So edge detection is a method to identify edges where you have strong changes in something. This comes originally from computer vision, where you have, for example, an image and you want to trace out, let's say you have an image of a person and you want to trace out the outline of the person. And you have quite a strong contrast between the background and the person itself, and that algorithm can identify where one object flows into the other. And you can translate this to climate data, where you look at abrupt changes from one point in time to another point in time. I'll explain this more in depth later. The second step in the workflow is then to apply a certain threshold. So we find places where you have a rapid change, but we want to make sure they are actually significant changes. So these are we call the abrupt shift. What we then do is we try to connect the regions that connect in space and time. So if we look at a single variable of a single model, we want to see like, okay, do we have a big region where we have an abrupt shift? For example, the whole summer sea ice disappears in a specific model. And this we call a large-scale abrupt shift. And finally, we try to relate this then to the global warming level at which this shift occurs. So back to the first step. So as I said before, this method was adapted for climate data. What specifically means it now works for spatial temporal data. So we have data that is two-dimensional fields. So they have a longitude, latitude, and they evolve over time. And the idea is that in here, you can find an edge. So there's a point in time and space at which you have a strong local gradient. So local change that is very strong. Now here I have an example time series of some fake data, where you can see at year 100, you have a strong increase in the variable. So this method is then capable of saying like, okay, here is an edge, here something happens. And one of the requirements for something to be an edge is that this gradient needs to be higher than the variability in some control simulation. And as mentioned before, we control this by looking at pre-industrial simulations. So these changes need to be at least bigger than the normal variability in a system. Now, secondly, this method finds these edges, but sometimes these jumps are relatively small. So you need some type of way to quantify them. And therefore, we use an abruptness measure. So what we do is when we are at the edge, we take a piece of the time series on the left and on the right. So that are these black lines here. And on those pieces of time series, you can calculate the standard deviation. And the second step, what you can do is you can define a distance between those two pieces of line. So we have a jump D, and you want to relate how big the jump is compared to its variability of the time series. That's what we do. We divide this distance by a sort of weighted average of those two time series. And then you use a certain threshold to say, okay, this is an abrupt shift. So this is a sort of more subjective choice. And to stay in line with the assessments that was previously done on the CMIP6 models, we use a value of 4, which sort of means that in case you have equal variance before and after the shifts, it means that your jump needs to be 4 times as high as your normal variability. So this is a really substantive change in your variables. Now, this method works quite well if you have relatively equal variance before and after. As you have here, the difference is only a factor 2. But some variables in some systems might have way bigger difference in variability before and after a shift. One example is a subpolar gyre where you have convection, and one of the variables to measure that is a mixed layer depth, and this is a highly variable variable, so that this changes by a lot. But as soon as the system collapses, you almost have no variability left. So that's, for example, an example time series here with very big difference in noise. So for the edge, you have around 6, and afterwards only 0.2. If you use the same measure as before, you get a very small abruptness value of around 2.4 in this case, which means it's not a significant shift. But as you clearly can see, this is what to our eyes would look like quite an abrupt change in the system, both in the mean state and in the noise. So for that, we introduced an extra correction factor, which is basically the difference between the noise before and after shifts mediated by some factor alpha. And we put this in the denominator of the abruptness measure such that if the difference is very big, it increases the abruptness. So in this example, without this correction factor, we only have an abruptness of 2.6, but with the factor, we go to 4, and this will be a significant event. A nice thing of this measure is that in case you have quite equal variance, then this correction factor is almost 0, so it does not do much. So it doesn't influence the results too much of the other systems. Now, what I've talked about so far is we begin with the data, we do this edge detection and find some edges. And these edges look something like this. If you only take one space variable, space dimension, you have these crosses, which are the edges, and white, there are no edges. So this is like just a common climate grid, and you have some time evolution. Now you could analyze only these individual edges, but they don't tell you much. For example, if sea ice disappear in one grid cell, it does not really signal an abrupt shift in the whole system. It might just be a small local change. So to fix that, we use some type of connected components algorithm to aggregate all these edges together. And we do that by looking at abrupt shifts that were found next to each other, either in space or in time. So in this example, you get 2 regions, region 1 and region 2. So these are not predefined areas in the analysis. We first find abrupt shifts on the level of grid cells, and then we create the regions out of them. And to make sure that these new regions are still abrupt, so that they don't cancel each other out, we do again the abruptness measure of this. So we check again whether this is significant. And these are called the large-scale abrupt shift. And what we say is that depending on the climate subsystem, the shifts need to cover a certain area at least for us to consider them in the analysis. So for example, for Arctic sea ice, we only look at abrupt shifts where at least 1 million square kilometers disappears as a single region. And finally, we want to say when these shifts occur. So for this, we take the global warming level in the simulation, the specific simulation we look at, at which we find the edge. And later on, what we can do then is, if we look at a certain variable and we have different models with shifts, we can then average out between the different models to get a certain indication of what the global warming level of the shift is. So this figure is just a general overview of like the results before doing the regional connected components analysis. So these are just abrupt shifts on the grid cell level of all variables together. And what this shows per grid cell here is the number of models, the fraction of the models that has an abrupt shift in that specific grid cell. Dark red, the very dark color is 70% of the models. And if you go to very light, it's 0 or 10% of the models. So as you can see, the biggest signal comes from the poles, especially in the north, which we also expected based on previous studies. The one done on CMIP6 is that a lot of changes occur related to sea ice. So this can be in sea ice concentration, but also related temperature variables, for example. And then we chose a number of subsystems of which we think, okay, here there might be interesting changes happening. So we have the Antarctic sea ice in the south. In the north, we look at Arctic sea ice, both winter and summer. And as a subset of that, also the Barents sea ice. Then we also look for the ocean variables. We look specifically at the subpolar gyre, so the stop of convection there. And then we have two systems that involve vegetation. So that is the Amazon rainforest and the boreal forest. And finally, we also look at snow cover at the Tibetan Plateau. Okay, now we'll go one by one through each system, starting with those that are designated as highly likely to be tipping elements. So the first one is the subpolar gyre. Here we have sinking of dense water from the south that is transported by the Atlantic circulation. And we have convection through the mixed layer. So we have sinking of water. And this is often measured by the mixed layer depth in these climate models. What's important to know that in this system, you have a lot of variability in the convection, which was one of the reasons of adapting the abruptness measure, as I told earlier. And the tipping in this system normally is like the seen as the collapse of convection in the subpolar gyre. And what we specifically look at is abrupt changes in the surface temperature. So if there is a strong cooling, or if the actual convection stops. Now the system is relatively localized. It's because convection itself is often quite a local process in these models. We focused on 4 different variables. So the first is the mixed layer depth, the direct measure of the convection, in which we found in 11 models at least some type of signal of collapse of the mixed layer. And on the right, you can see here one example. This is in the model MRI ESM2, where at the start of the year, you can see that the mixed layer collapses over around a year or 30. And this is southern of Greenland. Now, some other variables we looked at is the sea surface temperature and the surface air temperature above this area. And especially in the sea surface temperature, we found a lot of models, 22 models that have at least locally abrupt cooling. And this is more than were found in some other assessments. We also found 2 models in sea surface salinity. So this has really to do with the freshening of the surface and also the collapse of the model. And generally, these shifts happen at quite low temperatures. So the 90% percentile, if you average over all these models, is between 0.5 and 2.1 Kelvin. Next system is the Tibetan Plateau. Now, in CMIP6 models, the glacial dynamics are typically not represented. However, we can look at things like snow cover, temperature, and albedo in this area. And we find that if we look at these variables, that we find 12 models that have an abrupt shift. And this means like some type of abrupt disappearance. We found them mostly in albedo and snow depths, not so much in snow cover. But of course, if you have an abrupt decline in albedo, that is strongly related to the type of snow cover and the amount of snow cover. We find here on the right side, once again, another model example. This is sort of on the top, you see the connected components where we have 3 regions here that at different times show an abrupt shift in the snow cover. And as you can see in the figure, they are quite abrupt and they occur one after another. And if you look at the temperature range where this happens is between 0.5 and 2.5 Kelvin of global warming. Next system is permafrost. So we looked specifically at the northern polar permafrost in both Asia and North America. This is related to frozen ground. In the assessment in CMIP6, Drijfhout and others found one in the total soil moisture content, so the amount of water in the ground. So we looked at that variable, but we also looked at other one, which is the frozen soil water content. And this is a bit of a better measure of permafrost because it really measures the amount of frozen soil. And what we found in this system is not many big shifts, so not covering a lot of area in one component, but we found many local abrupt shifts. So here you can see one example. On the top, you can see Northern Asia, and all these grid cells that are colored are individual abrupt shifts. They all have the same color in this case. Bit below, the time series related to each of these shifts. And where you can see is a huge spread of when this happens, and they're all very disconnected. However, on the level of 1 to like 10 grid cells, this is quite an abrupt event. Now, I already mentioned that large-scale shifts are more rare. So in this case, large scale is more than 1 million square kilometers. So if we look at the left side of this figure, in the top one, we again have the frozen soil moisture content. And we divided here in a histogram the surface area of the large-scale abrupt shifts of positive and negative shifts. What we mean here with positive is an increase in frozen soil content, and with negative we mean an abrupt decrease. So that's the disappearance of permafrost. And you can see that the negative ones outweighs the positive, but there's only one model that has more than 1 million square kilometers as a single component undergoing such a shift. So that's quite rare. If you look at the total moisture contents, the image is not so clear because there are a lot of also positive shifts, so increases in moisture content. There are a few more that are really big areas, but the signal here is in that sense less clear. Another way to look at this, we only did it for this system, is to look at the total area of abrupt shift on the grid cell level, so without the connected components, just to see like, okay, what is the region size where locally you have a disappearance of permafrost. So we just add the area of all the individual shifts per model here, and then make a histogram out of that. And you can see again in the frozen soil moisture content, you have way more negative shifts, so a lot more disappearance of permafrost. And this area is add up to quite an extensive surface area of models reaching more than a few million square kilometers. The spread itself of when it happened is quite high. So between 0.6 and 4.5 degrees of global warming, do we see these shifts over the different models. The next system is the Amazon rainforest. This one is a bit more tricky. So first of all, there are only 7 CMIP6 models that actually have relatively proper dynamic vegetation modules. So for this system, we only analyze those. Someone else, Isabel Parry, did a study in 2022 that got published, and where they looked actually at these 7 models for abrupt shifts, and they focused their analysis mainly on vegetation carbon. And they found in almost all the models, they found some type of abrupt decline, covering different surface area between 0 and like 40% of the Amazon. Now for us, what's a little bit more tricky with the edge detection due to both the timescale and the variability of vegetation. First of all, the timescale of vegetation is longer than some of the other systems we looked at. which made it a little bit tricky sometimes for the algorithm to pick things up. But the second thing is also that the variability in this yearly time series is often relatively low in many of the variables for vegetations, which makes our abruptness measure work less ideal. Here you see one example, TIE ESM1, in the annual carbon mass in vegetation, so how much vegetation there basically is. And you can see that we do indeed spot a few regions that quite abruptly have some disappearance. So even though we could not do a very comprehensive assessment of this system, we can still see that we have many shifts partially in line with Paris. In the same variable, we do find less, but we scanned more variables. We scanned basically all the relevant vegetation variables, which you can also find in the paper. And we do find in almost every variable some type of abrupt shift. So this can also be things like the leaf area index or other measures of carbon in the soil. And the same holds a bit for the boreal forest. So what here can happen is partial decline of the boreal forest with climate change, but also a shift in the forest, so a northward shift due to warmer temperatures up north. So you get sort of a dieback at the southern edge, while you can get growth at the northern edge of these forests. So we looked again at the same models, and here you can see an example of the ECR3 model of leaf area index, so sort of an index of the amount of trees and vegetation. And you can see that we spot, in this case, quite a big region where you do have an abrupt increase in this leaf area index variable. So basically growth of the forest. But again, because the timescale variability is a bit tricky with the method we use, we don't make a precise assessment of the exact spread of global temperatures that this happens. But still, we can say that they're definitely there. Okay, the next section is about unclick tipping elements, which is about the monsoons and Antarctic sea ice. So we looked at 3 monsoon systems. It is South American, the West African, and Indian summer monsoon systems. And for this, we looked at the precipitation and latent heat flux. So we didn't look at specific indices for monsoons that also exist, because we just looked at the raw CMIP6 variables. And generally, we didn't really find any signal, nothing in South American, West African one. We found one example of a model in Indian summer. That's the IB ESM model, where we do see sort of a shift in precipitation, a more than doubling in the northeastern region. Not 100% sure what's actually the cause of this, but this is also the only model that shows some type of abrupt shifts in these precipitation and latent heat flux variables. Now, the next system is sea ice, and after this, we also talk about the Arctic sea ice, and these are actually the systems that show the most shifts. So the Antarctic sea ice is often thought to be potentially tipping elements, but also might disappear abruptly. And what we found is, if we look at this, the sea ice concentration is around 11 models, so relatively substantial regions with abrupt loss of sea ice. So on the right, we have CNRM CM6 model. And if you look at these individual colors in the above figure, that are the different regions that show abrupt shifts. And these are around 500,000 square kilometers up to a million square kilometers per piece. So around 11 models have around this size. And then we found 3 models that have more than 1 million square kilometers. And what you can see here nicely is that we have these 3 events. So the orange event is very early on, after 30 years in the simulation, while the blue one is way later. And we see this pattern in more models, where in one region, there's an earlier upstrip shift, which I can show nicer on the next slide. So what we did here is calculate these large-scale abrupt shifts. Then for each region, we gave it a global warming level. So we average all these regions or connected components of the different models of each other, so that you get a figure on the right. So on every grid cell, if there is more than one model that has an abrupt shift there, we average the global warming level at which it occurs. Where you have the hashed overlay, it means that there are at least 5 models at those grid cells that have a large-scale abrupt shift there. Now you can see that most of them indeed occur around the Weddell Sea, but there's another area around Amundsen and Rossi, and this is more like 3 models that are really extensive here. And we can see that in the Weddell Sea, the global warming threshold is quite lower, so the average in the region is 0.5 to 5 degrees. Well, if you look at the Amundsen and Rossi, the temperature is a bit higher. It starts only at 2.5 degrees. Now, a little bit of a caveat in this case also is that not all the models reach such high levels in this scenario at the end of 150 years. So it could be also that more models actually show these type of shifts in the Antarctic sea ice, but just not reach it. Moreover, it's also very seasonally dependent. So we can see on the bottom the number of models with such a large-scale abrupt shifts from January to December. And you can see that most of them occur around September, October, November. And this is also when the Antarctic sea ice is the most extensive. So of course you have the highest chance of finding these abrupt shifts. Finally, the non-tipping elements. So these are basically the rest of the Arctic sea ice. So I do the Arctic summer and winter sea ice together. These ones we denote as large scale if they cover at least 1 million square kilometers. And if we look purely at the sea ice concentration, we found roughly the same number of models in winter and summer that show these shifts, 11 in the summer and 13 in the winter. So on the right here, we have again 2 examples of the Easy Earth model and P3SM model. So the summer one is in September, so we can see a very steep drop, so that we have kind of complete disappearance of sea ice in roughly 20 years. The Arctic winter sea ice covers a bigger area because there's of course more sea ice, and this disappears a bit later, but also in a quite short time span of around 20 years. Now, if we look at all the models together, then we find that for the summer, it's between 1.1 and 3.1 Kelvin of warming where these shifts happen. And for the winter, it's substantially higher. It starts at 3.4 and goes to 5.5 degrees Kelvin of global warming. And we can do a similar thing as we did with Antarctic sea ice to look at like the spatial extent of these abrupt shifts. So this again averaging the warming thresholds of the large scale shift over all the models, but again the hash overlay being at least 5 models that have a shift in that area. And you can indeed nicely see that the temperatures in winter are obviously higher because they disappear later. In the bottom plot, we can see this global warming threshold spread out over the months. So this is a filing plot, which is basically a box plot, but then the width of the distribution at each level shows how much data there is. So it's sort of an extra weighted shape. So if you have a very thin tail, it means you have not so much data there. And we can clearly see that around summer, so August, September, October, when the sea ice is at the maximum extent, you have way lower levels of global warming at which the sea ice disappears than the winter. And if you just look at the annual average time series, you also find most events related to the disappearance of the winter sea ice. The final system is the Barents sea ice. So this is a subset of the Arctic winter sea ice. So this result is already taken into account in the earlier figures, but just as a zoom in, because it's often seen as its own system, we find quite often a shift here. Of course, the area is way smaller, so we also use a way smaller area threshold. But we do find at least 18 models that cover at least 0.2 million square kilometers. So this is again the ECR3 model, in which you can see relatively early disappearance of this Barents sea ice. And this also tends to happen at low temperatures, so between 0.5 and 2.9 Kelvin. Okay, so now we went, of course, quite fast through all the different systems. So let's recap and synthesize it a bit. So this figure sort of summarizes all the results I've been talking about. So we have now each subsystems on the horizontal axis, and on the y-axis we have the global warming levels at which these shifts occur. The filing plot is our data that we analyzed, while the dashed lines are from the assessment of Armstrong-McKay, so their assessment of warming threshold at which they expect either tipping or disappearance for each system. Now, of course, we look specifically at abrupt shifts, which is not necessarily the same as tipping, but in general, these processes might be related in many of these systems. And as you can see, there's quite a decent overlap between. For example, the subpolar gyre or the Arctic summer sea ice, they all fall relatively well within that range. But we also have a few examples that we find way wider spread. So one example is the Antarctic sea ice. In quite some models, we see it happening actually at way higher temperatures than in their assessment. Another noteworthy one is the Arctic winter sea ice. So they have quite a high assessment of roughly 4.5 to 9 degrees Kelvin of global warming at which that disappears. But we find it more between 3.5 and 5.5. And one of the reasons I also mentioned earlier is also because not every model in this ensemble reaches this high temperature, because it depends on how sensitive they are to CO2 input. So it could actually be that we would find more of these shifts in these models. Finally, we have with the 2 dots the Indian sun monsoon. So that are the 2 simulations of the same model at which we find the only shifts in the system. So that's why we don't have a filing plot here. So basically, they're either not present in the CMIP6 models, or they have to be calculated through some proper indices. And finally, we have the Amazon rainforest and the boreal forest, where because we didn't find a very consistent signal and we know that we missed some events, we chose to not actually draw for those systems a filing plot of the global warming thresholds. So that's why they're here not drawn. However, from what we do find, it's indeed quite a high spread in these models also. So that's the reason for that. And finally, on the top here, we have the proportion of models with at least one large-scale abrupt shift, dependent on at least the threshold that we chose. And we can see that we find quite a lot of shifts, mainly in the subpolar gyre, and in all systems related to sea ice. So that are the second to the 5th filing plots. That's definitely where we find the most shifts. Finally, a little bit of a thing more about this model sensitivity, which I mentioned a few times already. So one finding is that we find more of these large-scale abrupt shifts in models with higher climate sensitivity. So climate sensitivity here means how much do models warm for a given CO2 input. For this, there are 2 measures: transient climate response and equilibrium climate sensitivity. The transient climate response is actually a measure of the same scenario that we're using, the 1% CO2. So it says how much do you warm after 70 years of increasing CO2. While equilibrium climate sensitivity says what would your equilibrium climate state be if we double the CO2. But they are very similar measures. Now what I draw here is the number of models that have an abrupt shifts for each global warming level, divided in low, mid, and high climate sensitivity. So yellow is low, gray is mid, and red is high. So one thing that stands out is after around 4 degrees, you only see mid and high climate sensitivity models having abrupt shifts. And that's of course because low models with low climate sensitivity don't even reach those warming levels. So this is one reason why we find more shifts in models with high climate sensitivity. The other possible reason is also that models that are reacting have high climate sensitivity also warm more, which means other variables change a bit faster, which could also just lead to detecting more abrupt shifts with the methods we used. And you can see that a little bit back in the fact that these red peaks are also a bit higher around relatively low levels of global warming here. So to summarize, we find that abrupt shifts are quite prevalent in CMIP6. It's a bit difficult to compare to like a previous assessment of the CMIP5 data that Drijvo did, because we use slightly different methodology with an automated algorithm, etc. but it definitely seems that are still occurring, and also at relatively low levels of global warming. We can see them already in quite many systems. We should mention that we missed the dynamic ice sheet, so there are also systems in the climate that might show abrupt shifts that we could not assess. The simulation years are only 150 years long, so as I said, we missed some of these high warming events in models that are a bit slower in warming. And the setup of the detection that we did was suboptimal for vegetation. So there's definitely a potential for more abrupt shifts. And it depends also a lot on the input parameters and the thresholds that you choose, how much you exactly find, of course. But in general, we can say that we find abrupt shifts already occurring at low levels of global warming in quite some of the systems. The certainties remain still high, but we find still similar estimates to previous assessment. Thank you. Are there any questions?
Yeah, thanks a lot, Sjoerd. And please, everyone, go ahead with questions. I see Brian's hand is raised.
Yeah. Great talk. Thank you very much.
Thank you.
Could you go back to the slide on permafrost where you had the different trajectories? Yeah, one before that, I think. Yeah, here. Okay, yeah. So if I understood your conclusion here right, you said that largely you see many local, maybe you should say tipping points, but let's say, yeah, abrupt shifts, right, and the frozen moisture content, rather than one kind of global shift. Is that correct?
Yeah, exactly. Yeah.
That's also
yeah. Mm-hmm.
Yeah, I think that's definitely consistent also with other recent literature. So
exactly.
These orange lines, though, are these different locations? This is one model, and these are different locations. Is that right?
Yeah, that's right. Yeah. At first I had with different colors, but there were too many. So basically, every color here relates to a single point in the upper plot.
Okay. And was this behavior then also similar in the other models, or was it model dependent? Did you see some models where, because I think I saw on one of your slides you had like there were 4 models that did have a global kind of shift, right? Or
yeah, exactly. Yeah, so it's really model dependent what you see. I mean, that's holds for basically all the systems we analyzed. We do indeed see in permafrost many models that have like these small areas. This is definitely a model that has a bit more of these areas. So yeah, indeed, the pattern is the same, but it's still hugely varying between the models.
I would, I don't know how long this would take to look at, but it would be interesting to know if the behavior here is related at all to how deep the model represents the soil, because I think that models that have very shallow soil columns would be more likely to get, have a kind of warm bias and then have this kind of collapsing behavior. So that would be interesting to know.
Yeah, thank you.
But yeah, thanks.
I think the question that comes next is in the chat by Victoria Kola. Maybe, Victor, do you want to ask directly, or should I read it?
Yeah, I can ask it directly. So I was wondering on some models showing abrupt shifts and others are not. Can you somehow translate the ratio into some type of probability? And are there certain models that you find more realistic in maybe like a climate sensitivity perspective and so on? Yeah.
Yes, so I find it tricky to really translate it into probability, mainly because there are so many uncertain factors. So we already have that some of these systems are not fully well represented in these climate models. So you have a big uncertainty there. We also know there are certain model biases to either be too stable or not. So a real probability I find a bit much, but it does definitely indicate like it happens in quite a lot of models. So there's definitely something interesting. and take into account. Of course, what we did is a very general study of really just looking without going too much in the physical process of each model. So it's also definitely a good starting point for people who are interested in to look, okay, you see quite a lot of shifts happening in the systems. What is really going on in these different models? So I think there's definitely a lot to be found there. There's not a single model that stands out to me. There are a few models that just show consistently a little bit more, I would say. Well, of course, I already mentioned the one with the high climate sensitivity, just purely to the fact they reach higher temperatures and faster. But yeah, you need to really dive deep into model structure to be able to answer very specific questions on that, I think. So you should really focus on a single system for that. Yeah.
Thank you.
Yeah, thanks. Maya, you're next.
Yeah, thank you. So first of all, thanks for the really interesting talk. I mean, you answered part of my question now answering Victor, but I was like wondering about like, yeah, are there models that have more abrupt shifts and models that have less? Or, you know, are there models where all of their abrupt shifts are in the Arctic, and then models like, do you see this sort of like, you know, characteristic to models where like maybe they're like prone to abrupt shifts or not? Yeah.
Yes, good question. I find it hard to say now on the spot, especially. We try to look a bit into it. It's a little bit tricky because sometimes it's hard to exactly relate what model does what. Also, one of the issues we have, of course, is that many of these models are also related. So if you do the analysis, you really notice, for example, the SESAM models or the Easy Earth models that have a lot of shifts. But it's also because they have many like model types within CMIP6. So we already have like a bias of maybe 5 or 10 SESAM 2 models of different versions. And of course, they tend to have a little bit of the same trends. So I don't have the appendix open here, but in the appendix of the paper, we do also have a list somewhere where we list all the models with all the subsystems they have shifts in. And if you look carefully, you do see that models that are really structurally related do generally share the subsystems where you see abrupt shifts. So there's definitely a bit of a structure there. Yeah.
Okay, cool. Thank you.
And next is Victor Wolfkin.
Yeah, thank you. It's really nice analysis. I'm also focusing on the slide you show with land permafrost. As I think I agree with Brian that one part of its abruptness is related to kind of discretity of our land surface or vertical scheme. And I wonder, when we really try to model active layer depth in the models, we usually have a smoothing curve because of different thickness of depth layers. It's easy to see if a very shallow layer at the top, if it is ice is gone there, then it would be just on a large area, then it would be translated to a large area of changes. But it is really shallow. So I was wondering, indeed, how this is related to the shallowness of surface depth in particular. In CSM, a lot of area is also in really very high north with rocks. So basically, it is something like 30 centimeters of area. On the other hand, you have quite a big change here in the soil moisture. So I just wonder, is this feature of a shallow surface layer somehow reflected here, or it is more really a reflection of abrupt thawing of the area?
Yeah, good comment. Yeah, honestly, I don't know the answer to that question, but it's, I mean, definitely something that could be looked at. But yeah, I know, I mean, it's tricky. I think there are also some papers who delved a bit more into this. Yeah, I'm not enough knowledge for this specific system to really answer in depth, but at least it's indeed a good comment and something that could be looked at, because there would certainly be evidence. And I think it's also one of the questions I answered earlier, indeed, like, is it a probability that you have a shift if you sign to certain models? It's hard to say because you indeed have these model biases or model that don't model everything perfectly. So in that sense, I would see this as a really good starting point, again, to look in certain systems based on these findings to see what's really going on. Yeah.
One aspect which is not in CMIP6, but when people now look at TipMIP, for example, is reversibility. So if we just increase the temperature and when we go down, and whether this, let's say, ice in the soil is reversible, and we see in most of models it is reversible, at least at the surface. So surface temperature just goes back, but deeper layers, if a model represent them, so they stay intact. So there is some irreversibility there, which also count as a tipping trait. But I guess in CMIP6 it's really hard to say about this reversibility.
Yeah, very hard. Yeah, especially the scenario we look at. So we also really make the claim we find abrupt shifts, which might be related to tipping or not, or reversibility or not. But yeah, it's hard to say based on this data set alone. Yeah.
Yeah, thanks.
Thank you. And I see a question by Piero.
Yes. Hello. Hi, Sjoerd. Thank you very much for the presentation. I was just curious to know whether you tested a bit the sensitivity of all your results with respect to the thresholding that you chose on the definition of this abrupt shift. I know you might probably rely on previous work from Sebastian, but you also added this nice correction parameter. And I don't know if you had just an idea on how robust is the result with respect to a different threshold, for example. Yeah.
Yeah, that's a good comment. Yeah, so first one, there has been previous work. So especially for the edge detection, we took a lot of parameters from the paper of Battiani, but we also based some of these, for example, the abruptness threshold of 4, we also chose it based on the drive-out analysis because they used some type of a similar measure. So we tried to stay a bit consistent. We did do an analysis sensitivity on sort of Gaussian data and fake data with climate noise to really see indeed how does change this parameter influence it. And that way you try to optimize the best of both worlds. For example, if we have this correct, okay, let's see, yeah, we have this correctness factor for this indigo noise, and we did check a little bit whether this influences the result a lot. But what we see is correction factor does the job that it should do mostly. So it mostly increases the abruptness of this type of time series, but it does not affect at least too much the time series abruptness of more standard time series. But it's quite difficult to do a full sensitivity analysis on all the data because it's of course a lot of data. So we didn't go all the way there. So I would expect if people use slightly different methodology, they would find different things. But what we can say at least is if we look at the output of our algorithm, most of what we find, if we check it by eye, would definitely be what we're searching for. So always you miss events and you always get some events that are not really abrupt shifts. But I would say in generally it's quite consistent at least. Yeah, what we find. And except maybe for the vegetation systems in our case. That's why we only did partial analysis for that. Yeah.
If
Thanks.
I may add, yeah,
Mhm.
so the parameters do matter. I mean, that's the design. You have to tell the method what you look for. And so in that sense, it's not robust to the parameters, but it doesn't randomly change with the parameters. It's really monotonic. So if you decrease the threshold, you find more events, but they include all the events that you found for a higher threshold, right? So you just get more. So you can also start with a very extreme threshold, then you just get a few most extreme cases and you lower it and then you get more. So you can order them, for example. So it's not that problematic, but of course, yeah, it's some effort to filter through the data in this way, of course. Yeah.
Okay. Thank you. Thanks.
Yeah, maybe related, I also have a question. What's your opinion? In a way, we use a method that some genius master student designed in the 60s, this edge detection. You could also nowadays think of using some more advanced, sophisticated machine learning to tell us all kinds of events, but then, yeah, that would be perhaps not so easy to tell it what we want to find or to train it. What do you think? What could be the use of machine learning?
I think the lack of real training set is a problem. Like especially if we go in some machine learning type of classification. I think with this we also already had it a little bit. Like you don't really have a very clear set of this is an abrupt shift and this is not. So that makes tuning the parameters already difficult. Of course, you could generate a lot of fake data, but what we have also seen is that lots of this data looks quite messy. You are playing with a whole lot of variability or some sudden changes in time series that you don't expect. So I think that's difficult. Of course, there are now also a few other groups like working on some methods for basically time series climate data. It's also within TipMIP. So I think we'll also be interested to maybe just get an overview of a standard data sets, maybe taken from real climate data and just compare these different methods. And maybe see, maybe they can be combined in certain ways to get the strengths of multiple methods. That's I think quite exciting now. Yeah.
Thanks. Victor?
Yes. You found a little bit of a lower threshold for the winter sea ice. And I just wanted to ask a little bit more about what you found. If you saw like ice-free conditions for 3 or 4 months in the summer, did that warmth linger around long into the winter? Did it like this kind of freckled ice drift away in the transpolar drift, or what type of situations did you find there?
Yeah, I'm not sure about the exact mechanisms. Except indeed, yeah, we found them at slightly low temperatures. I'm not sure why. Would be interested to analyze in depth. But the problem with such a wide assessment is that we didn't go into the specifics of each simulation. So the real mechanism through which that happened, I'm not sure. But could be worth to look into. I mean, one of the interesting things is that you have these different blobs that go at different times. So yeah, that's definitely an interesting question. Yeah.
Yeah. Can I ask a follow-up question?
Sure.
Regarding the SPG, I believe you found like abrupt changes like in the pretty immediate future. Did you say 20 years? Something like this. What does this mean? Yeah.
Yeah, so it's with 20 years of the simulation. So the scenario we look at starts at pre-industrial temperatures and then goes up really quick with CO2. So the change happens in like a time frame of 30 years and quite quickly in the simulation. But that's also the reason we relate everything back to global temperature, because 30 years here doesn't say too much. But if you look at the global temperature, you indeed see that it happens at 0.5 to 2 degrees of global warming. And of course, we're already around 1.3, 1.4 now, or roughly whatever it is. So indeed, we do see in many of these models quite early on at temperatures that we are experiencing now already, we do see models, some type of collapse happening. Yeah. And of course, the cooling, which you also already can see the surface.
Yeah. Yeah. Do you expect personally to see like a North Atlantic subpolar gyre collapse in the next 20 years or so?
I mean, I don't want to claim, at least based on this, if it's going to happen. I would say at least the models don't exclude the possibility.
Yeah.
So at least in the models, it is possible. But of course, you need to take more information into account, like the actual data of the subpolar gyre right now and other type of models, not only this. Yeah.
Thank you.